course. Good. So it gives me great pleasure at this first seminar of the International Network on Quantum Annealing to introduce Matthias Werner from Qilimanjaro. So Matthias, do you want to share your screen?
Yes, I will do that. So if I'm not mistaken, you should see my screen now.
Yeah, we see, yeah, you're going into presentation mode now, I guess.
Yes.
Okay.
Now I hope you're seeing the presentations.
We see everything, we hear everything. So Matthias,
Awesome.
over to you. We're penciling in half an hour for these seminars, including question. We started a bit late, but you know, just over to you, I guess.
All right. Well, first of all, yeah, my name is Matthias. I work as an industrial PhD student at Qilimanjaro Quantum Tech in Barcelona in Spain. And yeah, it's a great pleasure and an honor to be the first speaker of the seminar series. And I will be telling you something about like a graph-theoretic analysis on first-order quantum phase transitions for adiabatic quantum computing. This is joint work between, well, me and my supervisors Arthur Garcia-Saez and Matthias. So first, to kick off, how do all these terms from the title, how do they tie together? So we're looking at the adiabatic quantum computing scheme, which I'm sure here most people will be very familiar with. But essentially, we have like a Hamiltonian that is parameterized by some interpolation parameter S, and we interpolate it between two Hamiltonians. One is called the driver Hamiltonian or the initial Hamiltonian. That will be the Hamiltonian at S equals 0, and the target Hamiltonian or the problem Hamiltonian, sometimes also called at S equals 1. And typically the driver Hamiltonian is some relatively simple Hamiltonian with a ground state that we can easily prepare. And the target Hamiltonian is somewhat more complex and usually encodes in its ground state the solution to an optimization problem that we're trying to solve. And if we interpolate between these two Hamiltonians slowly enough, then we have a decent chance that our system will remain in its ground state. And this way we can solve optimization problems basically. And here we will limit ourselves to like a particular class of problem Hamiltonians, namely those ones that we can write as diagonal matrices in the computational basis, let's say. And in this basis, the driver Hamiltonians that or the class of driver Hamiltonians that we will be investigating has a particular shape, namely this one. And yeah, so the shape is essentially that we assume that in the computational basis, we can interpret the driver Hamiltonian to be some d-regular graph G. So a graph that's just like a tuple that consists out of like a set of vertices and a set of edges connecting these vertices. And d-regular just means that every graph or every node in this graph is connected to d other nodes in the graph. So it has d neighbors. Simple just means that, okay, we don't have self loops in the graph. So yeah, every node has d neighbors, but it's not connected to itself. And these graphs will be represented by some adjacency matrix, which basically puts a 1 in, or basically it's like a matrix that where both each row and each column can be interpreted as one node. And if there's a 1 in a particular element, that means that these two nodes, they are connected by an edge in the graph. And we're gonna normalize that basically to just make sure that the ground state energies are kind of the same and makes it slightly more comparable. And by the minus sign, we make sure that the ground state is like the delocalized state in the computational basis. So just this product state of plus states. And there's a 1 over d just takes care that the ground state energy is always -1. And we will be looking at how the properties of this graph G, how those impact the annealing procedure. And well, what's the particular impact that we're looking for? Well, those are the first order phase transitions, which typically, which occur in the course of annealing when a particular phenomenon occurs, namely localization. And how does this work? Well, in the beginning of the annealing, the ground state is going to be in the delocalized state, which is just the ground state of the derive Hamiltonian. And as we tune from s equals 0 towards s equals 1, eventually the system the ground state has to localize. Ideally, it will localize in a global minimum directly, which will then give us the solution to our optimization problem, which like this green arrow process here. And this is typically associated with polynomially closing gaps and smooth solution fidelity. So the spectral gap is basically just the energy difference between ground state and first excited state, which basically limits the runtime of the algorithm. So if that's polynomially closing, we have like an algorithm that runs a polynomial time. And the ground state fidelity is like this right quantity here, which kind of smoothly, and it indicates how much the ground state basically, or how much solution the instantaneous ground state contains, let's say. However, this is not always what's going to happen. So sometimes the system is first going to localize in a local minimum and then has to tunnel through a potential barrier to get to the global minimum. And this is typically associated with an exponentially closing gap and a discontinuous solution fidelity, which are like the red arrows here and the corresponding red lines here in the spectral gap and the solution fidelities. And this can be kind of identified by having like a discontinuous solution fidelity. And which of these two processes occurs basically depends on the graph G and how the target Hamiltonian energies are distributed over the nodes of G. So how do we go about analyzing this? Well, we interpret our configuration space as like this graph, as indicated before. So each node in this graph will be a computational basis states, while each edge will correspond to an off-diagonal element, which in this case are contributed by the derive Hamiltonian. And within this graph, there's going to be a certain subset of nodes that we call V, that's going to have, or the energies associated with the nodes in this subset V are going to be nearly degenerate, which means they're going to be very close to some particular value, and we're just going to call this energy value either EV or ETV. And we're going to apply degenerate perturbation theory to figure out, like, to learn something about the energies as we tune, or as we interpolate between the driver and the target Hamiltonian. So just some notes on the notation. So the degenerate eigenvalue problem that we need to solve is this one here, and here the driver Hamiltonian HT has been replaced by HT prime. This is basically just the projection of HT onto V, and yeah, mathematically I'm going to be a little bit loose with what I call V. So V, I'm going to call both this subset of nodes as well as the subspace in Hilbert space that corresponds to these that's spanned by these computational basis states. Since basically there's a one-to-one mapping. And with nearly degenerate, like here's like a somewhat of a condition that tells us what I mean with nearly degenerate, namely if the target Hamiltonian wasn't completely degenerate on this subspace but had like small deviations, we assume that these deviations are relatively small compared to the impact of the driver Hamiltonian onto the energy eigenvalues. And now we have to solve this eigenvalue problem on this degenerate subspace, and which means we're looking for some eigenvector that we call like this ket V, and this will correspond to the principal eigenvector of the induced subgraph G. So the induced subgraph G of V, or like, yeah, the subgraph G V that's induced by the set V is basically these three nodes here in the blue in this cartoon, include or combined with all the edges that are connecting the nodes within the blue. So the edges that are going outside are not considered. And we want to find the energy ideally, so which will be the principal eigenvalue of this induced subgraph. And yeah, this induced on these eigenvalue problems we can now derive bounds on this energy eigenvalue. And there's going to be two bounds, namely an upper and a lower bound. The lower bound is shown here on the right hand side, and it's it depends basically on the maximum degree of this of the induced subgraph GV, and it can be relatively easily derived using Gershwin's circle theorem, applying this to the degenerate eigenvalue problem on the top here. And there's going to come with a corresponding upper bound on the energy, which will depend on some quantity which is called the conductance of V. And the conductance of V is a property of the subset of nodes in a graph. Namely, it's defined as such as the magnitude of the edge boundary divided by the magnitude of the set itself. So the edge boundary is, in this cartoon, is like the set of all edges that get cut by the dashed line. So basically all the edges that are leaving the set V and connect to other nodes in the graph, those are edges from the edge boundary. So in this case, we will have 1, 2, 3, 4, 5 cut edges divided by 1, 2, 3 nodes. And the conductance is a property, or the quantity from graph theory that has non-trivial lower bound. And non-trivial, by which I mean, okay, if there were no nodes in the subset, then I wouldn't need to cut any edges. So this quantity would be wouldn't make much sense. So it has to be a non-empty subset, and out of all the non-empty subsets of nodes from the graph, one of them is going to have maybe not necessarily one, but there's going to be one minimal conductance out of all the conductances that I can calculate. And this minimal conductance is called the Chiga constant. And this is sometimes also called the conductance of the graph then, and not of the subset. And it's basically like a property of the graph. And the Chiga constant comes with two inequalities called the Chiga inequalities. And the Chiga inequalities allow us to make connection between the Chiga constant and the spectral gap of the graph, which in our case we can use after tweaking the expressions a little bit to get a connection between this Chiga constant and the spectral gap of the driver Hamiltonian. And okay, so how do we reason about the occurrence or non-occurrence of these first order transitions? Well, we're gonna apply perturbation theory at least 2 or 3 times. And firstly, we will look at we will first treat the target Hamiltonian as a perturbation on the driver Hamiltonian. So the driver Hamiltonian is the one at s equals 0, and then start perturbing its ground state energy by slowly tuning in the target. And this will give us basically this green line here. And we do the reverse process for the target Hamiltonian and perturb both the ground state energy and the energy of a local minimum by slowly tuning in the driver Hamiltonian. And this will give us the blue line for the global and the orange line for the local minimum respectively. And how would we interpret this type of procedure, like this process now? Well, in the beginning of the anneal, the system will be in the delocalized ground state of the driver Hamiltonian, and we tune S, we tune S, we tune S, and eventually the system has to localize. And in this case here, we'll first localize in the local minimum, and if we keep tuning, eventually the system at this red star here has to tunnel and will then localize in the global minimum. So this type of plot here would correspond to this process where the delocalized state first localizes in the local minimum and then tunnels to the global minimum. And obviously, if the lines describing the energies of the local and global minimum never cross, then we're not going to get one of these localized transitions. But even if they cross, there may be scenarios when that would still not give us the first order transition, namely because the system is still going to be still localized when these lines would cross. So by the time the system then localizes, the global minimum energy will be below the local minimum energy, and hence we would never observe this localized transition. And so we would now be interested in finding these localized transitions where they are. And given the theory explained on the previous slide, using the bounds that we derived, both the bound that the upper bound on the energy that's based on the conductance and the lower bound on the energy that's based on the degree, we can now find bounds where these localized transitions would be happening. And now we have like a lower bound on this, where this localized transition is happening. That's what we call S star, which in the plots is always here this red star. And we're going to have a lower bound on this S star that's going to be dependent on the conductance. So we also call it the conductance bound. And we will have an upper bound that will depend on the degree. So we call it the degree bound. And about these bounds. So these bounds are actually equal. So these bounds are equal when the induced subgraph is regular. So if all the nodes in the subgraph have the same number of neighbors in the subgraph, then this graph is regular, and then both the maximum degree and both the maximum degree bound and the conductance bound will meet. And additionally, the lower bound will be asymptotically tight if the GV, so the induced subgraph, is a large Erdős-Rényi random graph. Which those are like basic results from graph theory that we kind of get from literature for free. So now, what do these bounds tell us about the first order transitions, and not only where they happen, but also can get conditions on if they will happen. So the perturbation theory results for the global energy and the delocalized energy, those are these expressions above here that on the previous slide I just say that they existed, but I didn't give the expressions, so here they are. And these two, so the E global and the E delocalized, they will be equal for some value of S as well, which we are going to call S prime. And if this S prime is larger than the upper bound of the S star, then we're safely in the regime where the system or the ground state would go from the delocalized state straight to the global minimum. And if this S prime is smaller than the lower bound on S star, then we are safely in the regime where the delocalized state would first localize in a local minimum and then would have to tunnel, which then one would definitely see a first order transition. And for an S prime that's in between these bounds, we can't really tell so far, right? Something that's also going to come up in the numerics is namely that under for certain problems, we might be able to assume that actually the graphs describing the local minima are actually regular, which basically means that if at least the low energy eigenstates, the low-lying local minima of our optimization problem, if they are basically well described by one of these two scenarios up here, then we can assume that the lower bound is actually a more accurate description of the energy of the local energy state. And then we can use the Chia constant actually to derive bounds for if we would expect to see localized transitions for this particular problem class or not. And using the Chia inequalities, we can then give these bounds in two flavors, once in terms of Chia constant from the derive Hamiltonian and once in terms of the spectral gap. So there might be some connections to symmetries of particular optimization problems, but that's ongoing research. So some other day we might be able to talk about this more. Just to give some numerical results. So we investigate our equations using some toy problem. Namely, we generate like a regular graph on random, and somewhere in this graph we place a very narrow global minimum, and somewhere else in the graph, in the disjoint region, we will generate like a randomly shaped and arbitrary deep local minimum. And then using the energies that we derive from perturbation theory, we basically obtain the following plots here. So on the left-hand side, we have one example scenario where we see one of these localized transitions. And first, let's look at the ground state energy, namely that it follows relatively nicely the predicted ground state energies that we get from our perturbation calculations. Here, the green is again the estimated energy of the delocalized state. The blue is again the energy of the global minimum state, and the orange is the region where we would expect the local and the energy of the state that's localized in the local minimum. It's gonna be, well, since we have only bounds on it and don't have it exactly, it's like a broad region. And the red shaded area is like the area in between the bounds that we derived. So as you can see, if we look at the solution fidelity, this discontinuity where the jump happens from the local minimum to the global minimum is safely within the region that the bounds would predict, as well as the minimal spectral gap is also in this region. Oh yeah, that's maybe a crucial detail that I didn't mention. So we're going to make the assumption that where this level crossing happens, this is also going to be where the smallest spectral gap will be. So that's kind of, we equate these two concepts, namely level crossing and minimal spectral gap, and this way kind of get like a bounce on where the minimum gap would be. And on the right hand side, we see like the same plots, now only for the case that we wouldn't expect to see a localized transition. So in this case, we get a very smooth solution fidelity and a much larger spectral gap. These problems we can generate at random, and if we look at various problem instances, we can predict where we would see, or like use our bounds to predict where we would see the minimal spectral gap, and we can compare that to the where we actually observe the minimal spectral gap. And we plot those two values against each other. So if so on the y-axis we have the predicted location of the minimal gap, and on the x-axis we have the observed location of the minimal gap. And if our bounds cross the diagonal, then it means that the observed value was actually within the bounds. So the color coding here is that the blue are the problem instances where we would definitely expect to see a localized transitions. The red coded ones are the ones where we would not expect to see a localized transition, and the orange ones are like the in-between cases. And we can see that we fairly well, our bounds fairly consistently cross the diagonal. And so we get like, fairly nice predictions from those bounds. And this phenomenon has been investigated before by Mohammed Amin and Vicky Choi in a paper from 2009 that's given here in the link. And they use second order non-degenerate perturbation theory, and using their predictions, those are the green crosses in this plot. We can see that they consistently are somewhat off, and they actually predict the level crossing to happen at way later values of S. And we believe that has a reason. Here in the plot that's taken also from their paper, they actually show here as a straight lines the first order non-degenerate perturbation energy corrections, and there's no level crossing, right? Because they start basically ordered and they all go to zero, so they would never actually cross. So they have to go to non-degenerate second order perturbation theory to predict level crossings. Otherwise, they only in second order they can see this effect. However, using degenerate perturbation theory, we actually can see this already in the first order correction. So this is why we kind of conclude, okay, the energy corrections that lead to those level crossings are actually like a first order effect, and not a second order effect. And this was a very simple toy problem that we construct like that. We can also, we compared also to the problem that Amin and Choi investigated in their paper, namely this weighted minimum independent set problem. So essentially, it's basically the same experiment, right? We construct a Hamiltonian that encodes this optimization problem, and we're finding the weighted minimum independent set, interpolate, and look where's the minimal spectrum gap. And here we then, using this, we can basically reproduce a plot that they also had in their paper, where they, for various problem instances of this weighted minimum independent set problem that are indexed basically by this WL parameter, which just gives like the depth of the local minimum. We can compare for these various problem instances the predictions versus the exact diagonalization results. So in red, we have the exact diagonalization. In blue, we have the second order non-degenerate perturbation theory. And this would be basically the plot from the paper. What we added now, like our graph-theoretic bounds, and we can again see that the lower bound actually matches, so the conductance bound matches very well the actual result, while the upper bound, the degree bound, is basically reproduces the second order non-degenerate perturbation theory result, which I think is not like a systematic phenomenon, but more like due to the structure of this particular problem instance. So it's more coincidence than systematic, I believe. But that's also, we have to look into this slightly more in slightly more detail. And yes, so for everybody who attended AQC, this was basically the part that you already knew. Now I'm also going to address some further research that didn't make it to the AQC presentation due to time constraints, but which still might be somewhat interesting. So how do we on time? 25, okay. So yeah, so this we're gonna in the graphs that we discussed previously, all these graphs had like very, very local structure to them. So now let's say in the limited case of having like a very dense and very highly connected driver Hamiltonian, what would we get? And so we're going to look at the most connected graph that you can think of, namely the all-to-all connected graph, which is also called the complete graph, which has an adjacency matrix that's given here, right? So basically, it's a matrix that's full of ones, except that it has a couple of zeros it has all zeros on the diagonal. And such an adjacency matrix can be decomposed to be written as such, namely as like 1D projector matrix, let's say, that can be decomposed into vectors, and then we just subtract some diagonal elements, right? And this structure already hints at that this is actually very similar to like this 1D projector driver Hamiltonian, which is a Hamiltonian that you would also see in the adiabatic version of the Grover search algorithm, right? So theoretically, this Hamiltonian has been used, although building this in a lab is a whole another story, because this would require very many highly non-local terms in the driver Hamiltonian. So this is more like a theoretical analysis for now, right? But anyway, we want to see if we can learn something about the eigenvalues and eigenstates of a Hamiltonian, of an optimization problem that uses this type of Hamiltonian as a driver, right? And we're going to do this by just looking at the Schrödinger equation, which I'm sure everybody knows. And in this, we're going to write the eigenstates, the instantaneous eigenstate, in the computational basis. So this instantaneous eigenstate, the index E signifies this is the eigenstate that belongs to the eigenvalue E, and the amplitudes that we use are like here indexed by Z. So those are the computational basis states. And the Hamiltonian, like the full Hamiltonian in using this projector Hamiltonian would now look like this. So we have like this projector part in front, and then some diagonal parts in the back. And for Hamiltonians like this, or more generally speaking, for matrices like this, there's actually like the so-called Sherman-Morrison formula, which tells us something about their invertibility. Namely, let's say here this is A plus U V transpose. That's basically the matrix or the operator that we care about. And U and V are vectors, and A is like some invertible matrix. And so this compose operator now is invertible if and only if this expression here, this 1 plus V transpose I inverse U, if that is not 0, then this compose operator is invertible. And well, again, Sherman-Morrison formula, well, it tells us something about invertibility. But actually more generally, and well, we were actually asking questions about eigenvalues, right? But the more general and more mathematically correct notion of eigenvalue problems actually, that it's like a question of non-invertibility of an operator like that. So we want to know is like all values of E for which this operator is non-invertible are like, is what we would call technically like an eigenvalue of the Hamiltonian. And so this basically allows us, if we identify the vectors u and v with basically these projector parts here, and then define the matrix A as basically this somewhat verbose expression here, then we can plug all this into the Sherrin-Morrison formula and just set it to 0, because this would mean it's non-invertible, and then we can solve for the eigenvalues, right? And this gives us an equation like this here in the bottom. So on the left-hand side, we just have this expression minus n over 1 minus s. And on the right-hand side, we have basically a sum of poles, basically. And this expression is still somewhat tricky to solve. It's not easy, but it implies some structure on the eigenvalues that we can exploit for our reasoning. So let's put a pin in that, and I'll get back to the equation in a minute, because first, let's see if we can also learn something about the eigenvectors that belong to this. So we have again here just the Schrödinger equation and how we would define the eigenvectors and the Hamiltonian that we deal with. And just plugging everything in and multiplying the Schrödinger equation from the left with like some computational basis states, we obtain an expression like this one here. So here's like the isolated amplitude of the eigenstate times some factor. And then here we have another term, but this sums over all the basis states. So this, if it sums over all the basis states, it actually doesn't depend on any particular basis state. So this is just like some constant. So this equation gives us the amplitude of the eigenstate up to normalization. So if we know the eigenvalue, then we can get up to normalization the amplitudes of the corresponding eigenvector. And now with these two equations here, again, I basically just for clarity perform like a shift of the energy scale, right? So basically shifting the energies left and right, which is physically and mathematically not meaningful. It just makes these, like, it's for clarity. These equations are now easier to read. So again, we have like the equation for the eigenvalues, and now it's much easier to interpret like the poles, right? And if we plot this equation, let's say reason about it graphically, just for sake of this presentation, let's say, we plot the right-hand side in the blue, which then is like here, for each eigenvalue of the target Hamiltonian, we have like a pole, and then in between is like the right-hand side of this equation as a function of the energy. And on the left-hand side, well, it doesn't depend on the energy, so it's just a constant. This is like the orange here. And eigenvalues are exactly all those values where these two sides are equal. So all these intersection points, those are the eigenvalues of our problem. And it's relatively easy to see, okay, there's going to be one lowest eigenvalue, right? Which is the ground state energy, which is here. And it's also relatively easy to see that this ground state energy is to the left of all the poles. It's to the left of the first pole, to the left of the second, and so on and so on. Which basically, in terms of equations, looks like this set of inequalities here. So this instantaneous ground state energy is smaller than S times the target ground state, smaller or equal to S times the target excited state, and so on and so on. And if now we combine this knowledge with the equation that we get for the amplitudes of the instantaneous ground state, then it's actually easy to see, okay, if we take the magnitude of these amplitudes, then the magnitudes of the ground state will be ordered as such. So the largest contribution to the instantaneous ground state will come from the target ground state. And then the second largest contribution will come from the target first excited state, and so on. And then basically in decaying order. And this basically means that, okay, the ground state is either delocalized, so all these amplitudes are relatively equal, with a slightly larger amplitude on the ground state, or eventually the system will localize if we tune S, but then it will localize mainly on the target ground state. So basically, that's the conclusion that we can draw from this analysis. The ground state localizes predominantly on the ground state of the target Hamiltonian. And some simple numerics to back this up. I'm just going to look at like a very simple Anderson model, where we take the annealing scheme again and take as the target Hamiltonian, like a diagonal Hamiltonian with randomly sampled on-site energies, let's say. And as a driver Hamiltonian, we try two things. Namely, first the nearest neighbor driver, which does basically the excitation can hop from like between neighboring sites, and we compare this to the all connected driver, which is the one we were just analyzing, right? And then we perform the annealing, which in the language of the Anderson model would basically mean that we tune the disorder from 0 to infinity, and we look at the solution fidelity of our ground state. And for the nearest neighbor driver, we can see that we get like this discontinuous jumps, where first the solution fidelity goes to 0 because the ground state localizes elsewhere, and then jumps up to 1, basically into the ground state, or into the target ground state. And basically these discontinuities are what we then would associate with those first order transitions. And for the all-to-all connected driver, these discontinuities don't appear. So these are the same problem instances, just once with the nearest neighbor driver and once with the all-to-all connected driver. And now we get all smooth solution fidelities, which basically shows, like, verifies numerically what we were arguing for analytically previously, namely that the localized transitions for this all-to-all connected driver are absent. So with that, I'm basically through. Just a quick summary and also some points for further research. So we looked at the investigate the origins of first order quantum phase transitions in the quantum or in the adiabatic quantum computing scheme, and found that we can relatively well describe them using quantities from graph theory and analyzing like the structure of our problem. And using graph theory, we can actually derive some bounds on where we would expect to see the minimal spectral gap, and under which circumstances we would expect to see localized transitions at all or not. And if also, it's somewhat more speculative, but if we are allowed to assume that our low energy states are fairly well described by somewhat regular graphs or Hamiltonian graphs, then we can also get bounds on when we would expect to see localized transitions for entire problem classes. And obviously now not obvious necessary, but further research that would be interesting would be to analyze like the relation to symmetries, as well as extend this analysis to investigate the mechanism of how catalyst Hamiltonians work. Voila. Oh, the slide didn't load, try loading. Okay. Not sure anyway. Okay, well, that's not too bad. Yeah, sorry for the technical difficulties, but in the second part, we basically just show that if we have like a very densely connected all-to-all driver Hamiltonian, then we wouldn't see localized transitions. And since this is more like of a theoretical point, it would be interesting to further investigate whether or not this effect actually persists also for long-range interacting Hamiltonians, and also how this would be experimentally feasible, because it's on paper that's easily written down, but built in the lab, that's a completely different story. And the part of the slide that's now not loading are basically a couple of papers, or titles of papers that I put here, where long-range interactions are investigated and created by various mechanisms for various platforms like ion traps, and by, for example, fancy couplers, or also Floquet engineering. But unfortunately, that I guess you don't see right now. And with that, I thank you for your attention. I apologize for going over time slightly, but nonetheless, I hope you forgive me. And I'm looking forward to the questions. Thank you.
Good. Thank you very much, Matthias. Thank you for a very interesting talk. We certainly forgive you for overrunning, and I'll open it up for questions. So anybody have any questions for Matthias? Either raise your hand or speak up or put something in the chat. So maybe I'll start. Could you go back to your non-local driver slide where you're comparing the nearest neighbor? Yeah, this slide.
Yes.
So I guess I'm instantly thinking about what is the sign of your magnitude of your interactions is. So these are pairwise XX interactions, I guess. Have I answered that correctly? And then I start to think about stochasticity and non-stochasticity. Could you comment on that and whether the sign of that pairwise driver is making a difference?
It will make a difference here in basically everything we looked at so far. The driver Hamiltonian was completely stochastic, which is kind of a consequence of the assumption about that we take the driver Hamiltonian to be proportional to the adjacency matrix of some graph. So for it can be extended to non-stochastic drivers as well, although then the bounds get slightly looser, and well, that's an ongoing work, so I'm not going to say too much.
Okay.
I also don't know yet. So I toyed around a little bit with non-stochastic drivers, and the bounds get looser. That's the main effect that happens. I haven't figured out yet how to get them to be tighter.
Okay, interesting. Good. There's a question from Elliot Capit in the chat, which is, how hard would it be to apply this analysis to embedded problems? For example, where single variables are replaced by chains to map larger logical problems to 2D grids on quantum hardware?
Mm-hmm. Interesting question. I assume you mean like the how to applying the all-to-all connected driver, right? Oh, wait, let me check in the chat actually.
Yeah, I guess the question, Elliot, if you're there, is whether we're thinking about the driver graph or the target graph in your question.
I'm thinking more of the target graph. The all-to-all driver sounds a lot harder to implement real hardware, obviously. So I'm thinking about, like, this sort of standard transverse field plus problem along Z case.
Yeah. Okay, interesting question. Embedding. So if we have like the standard transverse field driver, first of all, like the graph of the driver will be like a hypercube, right? Which would bring already a couple of interesting features with it, I believe, or at least some knowledge that we might be able to understand, or that we should understand better. And in terms of having like an embedded graph for the target, so I never thought about it actually. So it would basically mean that flipping one logical bit would correspond actually to flipping several physical bits, which I assume would make the basically put something that's very close in the logic problem very far apart in the physical system in terms of how close they are on the graph that's induced by the driver Hamiltonian. So it should not. Yeah, it should generally make the problem complicated more. Like, it's not going to make it easier. That's the only thing I feel comfortable saying, actually.
Okay, there's a question from Alexandra Zagoskin in the chat. There seems to be always 100% success probability.
Yes.
Is it due to some special properties of the Hamiltonians you consider?
No, I mean, what I'm analyzing, I basically analyze the ground state properties, right? So I don't analyze the actual annealing procedure. So those are just the analytic solutions, or the exact solutions to the ground state of the Hamiltonian at any given time.
The static solution, in other words.
Yeah, exactly.
Not dynamic.
No. Then I haven't applied this yet to like actual simulations with errors and whatnot.
Any additional questions from anybody? Maybe I can just ask another quick question then. So I guess you know, one of the central questions in quantum annealing is how to avoid these first order phase transitions. So do you think there are pointers from your graph theoretic analysis that if you've got some problem graph defined on a graph, that you can maybe add something to it in a targeted way that will eliminate these first order phase transitions? Or is that too much to hope for?
So generally, I don't know. For particular instances and particular some edge cases, maybe yes.
Okay.
So maybe if we particular those cases here, the orange ones, where the bounds basically don't really tell us if there's going to be a transition or not, because we already know. They basically correspond to scenarios where let's see, where can I illustrate this? Where yeah, the orange, like the target, like the gap of the target Hamiltonian is relatively large, then this red star moves closer to the green line over here. So basically that's what is yeah, the localized transition moves further to the center. And for example, one way where then these type of problems, for example, could be, or where the first order transition in this type of problem could be avoided is, for example, by something as simple as introducing even a stochastic catalyst, that if we're a little lucky, the effect of a stochastic catalyst will essentially be that the delocalized energy will turn from a straight line to like a line that's kind of yeah, turns into like a parabola that's with that's kind of coming down a little bit further, right? And if that effect is stronger on the delocalized state than it is on the localized states, then the localized transition would be very close. Then this little bit of extra curvature might allow you to get to the regime where you would avoid the first order transition. For example, that would be one thing for some problem instances that might work. And yeah, that's, for example, one thing that would follow from this.
Good, thank you very much. So I guess we've badly overrun, for which I blame the chair of this session. But let's thank Matthias one more time. And I'll even give a personal round of applause. Thank you, Matthias, for a very interesting talk. And just a reminder that, actually a couple of reminders, if anybody would like to give a presentation, they have some new results that they'd like to share or some ideas you want to share, please do drop me an email. We've got an ongoing series of talks, but of course, one of my main jobs is to find speakers on a regular basis. So please do send me an email if you're interested in doing that. And a reminder, the next presentation is in 2 weeks' time with Anna Banerjee. So thank you very much for coming today, and thank you to Matthias, and we'll see you all in 2 weeks' time. Thank you.